Okay, this video is going to show how you can integrate PySulfSat with a Python package, PyMELTScalc. So this MELT stuff relies on the Python MELT architecture developed by Paula at Caltech. So the first thing you're going to have to do is you're going to have to download the MELT Python infrastructure from Paula's Caltech website. And then what PyMELTScalc does is it basically takes that code and it has written nice functions for allowing easy fractional crystallization to happen. So you can click on this GitHub link to learn more about PyMELTScalc, because you're going to have to install that as well. So we will kind of go through that. As in the Petrolog video, which I recommend you watch first, you can get this notebook off the Read the Docs page, and you can get the data that we're relying on from GitHub here. If you haven't done so, you're going to need to install PySulfSat using this pip install function, so you can just remove this comment. And then you're going to have to link to your path where you put the MELT stuff from Paula. So here is where I put it on my computer. And then the final thing you have to install is the PyMELTScalc thing. So again, I've installed it on my computer already. You only need to do this once, but you can uncomment that and run it. So now we're importing NumPy, Pandas, Matplotlib, PySulfSat, and PyMELTScalc. And you're going to want to get the version each time. This is useful if you're communicating with myself for PySulfSat, or for MELT problems with Matthew Gleason, who wrote this. So that can be very useful, so we can help you troubleshoot. So the first thing we're going to do is we are going to load in the data. So this is basically just a load of oxides that I measured on the microprobe. And PySulfSat wants to know what phase it is. So because these are just like SiO2, MgO, FeO, we're also adding this suffix underscore liquid so that we get it in the right format. And then what we're doing is we're choosing a single starting composition. Here I'm just choosing the first row in the file, and that's what we're going to feed into MELTS. So now we're using the PyMELTScalc function, so we're using m dot rather than ss dot. So here we specify what type of MELTS we want to use. So here 1.0.2, we want to use 10% iron 3+. This is the sample here that we have loaded in. We want to fractionate solids, we want to fractionate fluids, we want to start at the liquidus, and we want to continue until 750 Celsius with a temperature step of 5 Celsius, and here we are running at 1,000 bars, so 1 kilobars. This will take a little bit of time to sort of initiate, but what it's going to do is it's going to return a dictionary containing a series of data frames. So basically there is a data frame for each phase, and then there is also this data frame all, which contains sort of all the information you might want with these sort of phase identifiers. So you can see you'd have SiO2 liquid, you also have SiO2 olivine, and for whatever phases you have. So we can extract this data frame from the dictionary, and we're going to call it MELTS. And this is what we get. Basically, it's a summary of everything we need. You might want to see what phases have crystallized. So here we're just looking for the columns that contain silica, and this will tell us sort of all of the discrete phases. So there we go. And you might want to know how many rows have calculated. This is just some timing, so don't worry too much about this. But what we're going to do now, this is basically showing that it takes about, the SCSS calculations take about 0.7 milliseconds per calculation. These are extremely fast. So now we might want to calculate the SCSS using Li and Zhang 2022. So now we feed in the data frame, which is MELTS. We feed in the temperature, which is MELTS in Celsius plus 273.15. We need the pressure in kilobars, so again the pressure we told it to divided by 1,000. Feed in the water content, estimate a sulfide composition, and estimate a Fe3, Fe total, which again is from MELTS. So that will run like that, and that's all fine. So you have, you can look at what this looks like by using head. There we go, so we've calculated the SCSS for a MELTS model. We can also do this using the Smythe model, so we're going to run this. So you can see again, here you go, and say you want to plot magnesium against the SCSS that you have calculated. Well, there you are. Similarly against iron. And then the rest of this notebook just shows using other calculator. So basically, once you've got your MELTS model, it's in oxides, it's exactly the same format that PySulfSat is expecting, so you can run any of the other calculations that you want with that.